And so E is equal to m naught c squared plus half. Whoa. Where did that come from? Well, let's start from the beginning. Well, today on Physimathizer, we're going to be exploring the relationship between Einstein's most famous equation E equals mc squared and the regular kinetic energy in classical mechanics. I'm going to be using the Feynman Lectures Volume 1 as a guide. This is Chapter 15 of Volume 1, though I'm kind of working the proof backwards. Well, the Lorentz factor is what is 1 over the square root of 1 minus v squared over c squared. It's some factor that you multiply some quantities with in special relativity to get the associated quantity relative to a moving body with speed v. And so the mass of a moving body with speed v is equal to its rest mass m naught over the square root of 1 minus v squared over c squared. I'm not going to prove it here, though Feynman proved it beautifully in chapter 16 of the book, using just studying a case of collision and using a change of coordinates or a change of frame of reference. Well, we start by moving that square root to the other side and squaring both sides, and so we're left with m squared times c squared minus b squared is equal to m naught squared times c squared. Oh, and I multiplied everything by c squared. Developing this, we get m squared c squared is equal to m squared v squared plus m naught squared c squared. Well, we notice that the right term, which is m naught squared c squared, is just a constant a, since the rest mass of a body never changes and the speed of light is a constant. We can say that a is this m naught squared c squared just by plugging in v equals to 0 in this yellow equation. Well, we differentiate both sides with respect to time. We get that the derivative with respect to time of m squared c squared is equal to the derivative with respect to times of m squared v squared plus the constant a. So we're left with c squared times 2m dm dt is equal to 2mv times d of mv dt. We cancel the 2m on both sides and we're left with c squared times dm dt is equal to v times the derivative of mv with respect to t. Let's put that on the shelf, and we notice that the momentum is equal to m times v, and since c squared is constant, we get that the derivative of m times c squared with respect to time, which is just the left hand side, is equal to v times the derivative of momentum with respect to time, since the momentum is equal to m times v. And since the force is the rate of change of momentum with respect to time, and since energy is defined as force times distance, or work is defined as force times the displacement in the direction of the force, we're left with that the derivative of energy with respect to time is force times velocity. And so the right hand side in the green equation is just the derivative of energy with respect to time. So we get that the derivative of mc squared with respect to time is equal to the derivative of E with respect to time. And so energy plus some constant c is equal to mc squared. Well, by plugging v is equal to 0 in that equation, we get that constant c is just m naught c squared, which is the rest mass times the square of the speed of light, which is what stands for the rest mass equivalent of energy in the body. So we replace that whole e plus c with just an e, and so we're left with E is equal to mc squared. We did that because we say that the rest mass of some body is just a part of its bigger energy, a part of a total energy. So when we rename E plus C, we get another E, which is this time the total energy, and this is equal to mc squared. Well, how does classical mechanics fit into this? Well, let's remind ourselves of the Lorentz transformation, which is m of a body moving with speed v is equal to its rest mass over the square root of 1 minus v squared over c squared. And now we know that the energy is equal to m times the square of the speed of light. And so E is equal to m naught c squared over the square root of 1 minus v squared over c squared. I'm going to put that square root on top in just the parentheses and replace the 1 over the square root with a power of negative 1/2. And I'm going to develop that using the binomial theorem. And so 1 minus v squared over c squared all to the power of negative 1/2 is just 1 plus a half v squared c over c squared plus 3/8 v to the fourth over c to the fourth plus 15 over 48 times v to the sixth over c to the sixth, and so on. Well, to get the energy, we just multiply that by the rest mass times the square of the speed of light. And so developing those, we get the energy is equal to m naught c squared plus a half m naught v squared plus 3/8 m naught times v to the fourth over c squared, and so on. Well, we can see that the terms on the right are not that relevant compared to the two terms on the left, m naught c squared and half m naught v squared. Since for small velocities, all the terms beyond 1/2 m naught v squared just have a c to the power of 2 or higher in the denominator, which is just so close to 0 that we can ignore it for small speeds or small velocities. And so we can say that the energy is approximately equal to the rest mass of some body times the square of the speed of light plus a half the rest mass of that body times its speed squared. Well, the left term m naught c squared is just its rest mass times the c squared, which is just the equivalent of its rest mass when transformed into energy. The right term, however, is what stands for the kinetic energy in classical mechanics. And so we can say that the energy of some body is approximately equal to its rest mass energy when in relativity, when energy and mass are interchangeable, plus its kinetic energy, or what stands for its kinetic energy in classical mechanics. Of course, there are some additional terms, the 3/8 m naught v to the fourth over c squared and so on, but those are extremely tiny in comparison to the two terms m naught c squared plus a half m naught v squared. That's how the energy in classical mechanics fits as being part of the bigger mc squared energy in relativity. Well, thank you. If you liked the video, don't forget to like and subscribe, and until next time, go Physimathize the world.